chapter, right? The electric potential energy. Let's derive the electric potential energy using the gravitational potential energy. They have the same steps. Why they have the same step, the same form? Because both use a conservative force, right? The conservative force says that the work done, right, by the field between 2 points doesn't depend on the path. Depends only on the initial and final position. Okay, let's start with the gravitational field. Right, imagine that this is the gravitational field is constant, or this is the ground, and we have a particle at this position YB, and then because of gravity, right, moves to this position, right, position Y sub B. This is one Y sub A and Y sub B, correct? Right here. Perfect. We have a mass, and the force is the gravitational force. Now let's find the work done by gravity. The work done by gravity is equals to force. We have the dot product between these two vectors. We have again our displacement in that direction too. Now what do we have then? Because they are parallel, remember this is defined as F, right, cosine theta delta y. But what is the angle between these two vectors? It's 0, so cosine 0 is 1, correct? So it's actually just force times delta y, correct? Perfect. And what is the force acting in this case? Gravity. Equals to mg. And what should be delta y is the magnitude, right, of this delta y right here, right? Which is gonna be the distance. It's gonna be then y sub a minus y sub b, correct? Y, right, a minus y b. And then this is equals to mg y a, right, mg y b. And then we define, remember, the gravitational potential energy to be equals to mgy. When we write this definition right here, what do we have? This equals potential and gravitational potential energy at A and gravitational potential energy at B. It's better to represent this as a difference, right? The change. So we represent then the work done by gravity on this object is equals to negative the change in the gravitational potential energy, correct? Remember, this is the gravitational field. Let's do the same thing using an electric field, okay? So this is the electric field right here, right? Is constant, the same thing as for gravity, okay? Imagine that right here is a negative plate, right? And right here we have, imagine, right, a positive plate. And we create in this way kind of a capacitor, right? A constant electric field. And they do the same thing as for gravity. In this case, we use a test charge, right? Q naught in this electric field. And then later, of course, gonna be right here, gonna be accelerated with that force. And also we have right the displacement delta y. The same thing as for gravity. Let's find the work done by the electric field. Okay, let's do it. So the work is equals the same thing, right? Force, the dot product of these two quantities. And this is equals to, what is the force in this case? The electrostatic force. Remember, this is coming from, and it's related to the electric field. That is, I remember how do we define the electric field? The force divided by Q naught. From here, right, the force equals just to Q naught, correct? Similarly to, again, gravity, gonna be Q naught, the electric field, times y, what? A minus yb. The same steps. And then this is equals to Q naught E, right, y A minus Q naught E, right, yb. The same thing as for gravity. We defined, look, we defined the electric potential energy to be equals to Q naught E times y. Correct? When we substitute this value right here, what do we have? It's gonna be electric potential energy at A, right, minus electric potential energy at B. If we wanna use the change as for gravity, we can do it too. And we get the same form, right? Remember, they have the same form. Equals to negative the change in the electric potential energy. Okay. Also, look, the work done by gravity, or the work done by the electric potential energy, well, the work done by the electric field doesn't depend on the path, right? It depends only on the initial and final position. Let's show this part right here. Imagine that we have this position right here and this position right here, right? Imagine again this is and the torque height is h. Okay, we have a mass right here and we release it, correct? And we're looking for the work done by gravity from here to here. Okay, let's do it. Also, we're looking for the potential energy. Okay, perfect. Now, what should be then the work done? One more time, taking this path. This is h. Okay, this is gonna be initial position, right? Final position. That's the force, correct? So it's equals to what? Mg. One more time, it's gonna be YA minus YB, correct? But what should be YA, right? Or YB? YB is gonna be, what should be actually a delta Y? Delta Y is just H, right? Delta Y is gonna be H, okay? So it's gonna be equals to MGH. Okay, perfect. Now, let's go to, this is the magnitude, okay, it's H. Now let's go to this path. Let's see what happens when the particle moves right to this path. Now this path, the length is gonna be L. Of course, we have this angle theta. So the particle is always acting by this gravitational force. Correct? Now let's go back to finding the work is equals to, again, the same product, right? This is equals to, okay, force cosine theta delta y. In this case, it's not delta y. In this case, it's gonna be what? Delta L, right? Delta L. And change L, right? Delta L, correct? Delta L. Delta L. But what is delta L? Delta L is gonna be just L from the torque path, right? The torque path. Let's take it L, right? L, the torque path. Perfect. Now, what should be the force? Well, the force is just mg, right? So mg, again, this is the work done, is equals to mg, correct? Cosine theta times L. But from the figure, from this triangle, what do we have? Cosine theta is equals to adjacent over hypotenuse, which is h over L, correct? From here, h is equals to L cosine theta, which is the same as this part. So work is equal also to mgh. So in both cases, we have the same answer. So that depends on the path, right? The work done depends only on the initial and final position. The same thing happens to the electric field, right? The work done by the electric field doesn't depend on the path. It depends only on the initial and final position. We can do the same steps, right? Taking out this path from here to here, and we follow the same steps over here because they have the same form, and we get, right, that the work done doesn't depend on the path. Depends on the work done by, of course, the electric fields, right? Depends only on the initial and final position. Okay, perfect. Also, we can involve right here the net work done, right? The net work is equals to, we know that from mechanics, right? The net work is equals to the change in the kinetic energy. Also, when we have, look, kinetic and potential, these two quantities are related under the conservation of energy, right? So right here we can use also conservation of energy, right? Means kinetic initial plus potential initial is equals to kinetic final plus potential, right? Final. Correct? Initial, final, correct? Final. So this is the conservation of energy. So we can use it also for cases when we involve, right, the electric potential energy. Correct? Perfect. In this case, we can go back again to, let's say, work, right? Work is equal to negative what? The change in the electric potential energy, but the electric potential energy, but the work is equal to what? Also work. work. How do we define work? Well, by definition of work, work again is equals to force times what the dot product delta y, for example, in this case, for constant electric field, correct? So this is equals to what is equals to Q naught electric field times what? Times delta y. We can call it right delta y. Or delta y is just the distance, correct? It's equals to Q naught E times the distance between the 2 points, right? This displacement, the magnitude, we call it the distance, correct? Then from here we have that the change in electric potential also is equals to negative, right? Q naught E times D, correct? Perfect. In this case, we're involving a constant electric field. So what happens if the electric field is not constant? Let's say the electric field produced or created by only one charge. Okay, let's do it. Let's do it. When we have the electric field produced by a point charge, right? We are looking now for the electric potential energy, right? Electric, right? Potential energy, correct? Of 2 point charges of, right, 2 point charges. Okay, let's do it. Let's find the electric potential energy, right, of 2 point charges. Okay, let's do it. Imagine that we have this positive charge right here. Remember, the field goes right radially toward all direction, right, from the charge. Imagine that we're taking this path from here to here, right? At the beginning, this is the initial position, R sub A, and later this is the final position, right? From here to here, R sub B. And right here we have the test charge, correct? This is point A and point B. Okay, now how we can find then the work done by the field of this charge on this test charge? Okay, let's do it. Work, because this is a linear path, right? We can use the linear integral, right? So it's equals to the work done from A to B is equals to the integral from R at A or R sub B, right, of this product, correct? It's gonna be this that product. And because the force, right, is parallel to the direction, correct, of the radial vector, so the angle is 0, so cosine 0 is 1. And then this is equals to just equals to the integral, right, from R sub A to R sub B, right, f dr. Correct? Perfect. Now what is the force acting? Now we have the work, right, from A to B is equals to this position to this position. What is the force going to be? K, what else? K, Q, Q plus times Q naught over R squared. Then what should be this integral? dr. And what should be this integral? It's going to be K, Q, right, Q naught, correct, times 1 over R negative from initial position to final position. Correct. And what should be then this work? The work, right, from A to B for a 2 point charges, correct, is going to be equals to K, right, Q naught times 1 over RA minus 1 over RB. And in this case, as before, right, we can call this the electric potential energy, right, for a point charge. So from here we can call this the electric potential energy for point charge is a K, Q, right, Q naught, correct, divided by R. So we define, again, this is for point charge, K, Q naught over R as the as the electric potential energy, correct, for this point charge. Now, when we substitute this value, this condition right here, what do we have? Well, this is equals to, let's continue this analysis. This is equals to the electric potential energy at A minus electric potential energy at B. Or we can change it, right, to have the change equals to negative, right, the change in the electric potential energy. And we go back to the same equations as right here for a point charge. Perfect. Now, we mentioned that the path doesn't depend on the word doesn't depend on the path, it depends only on the initial and final position, right? This is okay in a straight line. What about the path changes? Okay, let's do it. Imagine that now it goes from here, right? Let's use the same picture right here because I don't have too much room. Okay, imagine that these are the line of force, correct? Now we start right here and we end right here, right? And we are taking this path, imagine. Okay, now let's take these points as a reference. This point, for example, correct? This is the electric field. So we have that this is the displacement, the L, right? This is the vector in the direction of the radius, right? The R, and we have then right here theta. Correct? This is point A, this is point B. Perfect. Now let's try to, this is the L, correct? The L, this element, that section, right? The element of the path, correct? Now, the same thing as before, let's find the work done, right, by the electric field from here to there. Okay, let's do it. So the work done from A to B is equals to the integral, right, from this position right to this position, correct, A and B of this this product, correct, and this is equals to, one more time, the integral, right, from A to B. The beginning is from A to B, correct, A to B, okay, of what? Of this product, which is F cosine theta dl. Correct, but from the figure, this is theta, from this triangle we have that cosine theta is equals to dr over dl. From here, dl cosine theta is equals to dr, correct? So this is equals then to, this is from A to B, from A to B, gonna be the integral, correct? The integral, right, now this quantity f, right, dr from this position to that position. And we get to the same position as before, right, in a straight line, correct? And the answer is the same, right? The answer is the same, correct? Well, let's continue right here. It's gonna be right this the integral of these charges, right? In case you forgot, okay, k q naught over r squared dr. And from here, right, we get the same answer as this condition, right? Got it? This is for a point charge. Now, what should be the, let's do the graph for the electric potential energy. Okay, let's find that graph. Electric potential energy. And compare that to the force, right? Remember how we're dealing with electric force, right? Force, remember force, according to Coulomb's law, is equals to K, Q, Q1, Q2 over R squared, correct? So we know that this is the path for this force, right? This is the force between two charges, right? If the charges are the same, right, we expect that curve, right? This is like charges, like charges. When we have unlike charges, correct, we expect this curve, correct? This is unlike charges, unlike, right, charges. What about for potential energy? Remember, force is proportional to r squared, and potential energy is proportional only to r. So they have about the same form, right? About the same form. Now this is electric potential energy, of course, is against r, right, against r. So in this case, it's gonna be like that, right? It's gonna be less steep, right? Stepped like this, and the other one gonna be like that. This is for a potential energy, correct, for like charges, and this is for unlike charges. See, to compare these two graphs. Also, let's see what happens to zero. Remember, when we're dealing with potential energy, like in gravity, we mentioned that when we have constant field, like on the ground, right, we call this a potential energy to be zero, correct? What about for this case? When is this electric potential energy zero? Well, when the distance is at infinity. When the distance is at infinity, right, the electric potential energy is zero. But what happens for this case? When we have the constant electric field. Remember, when we have constant electric field, right, we take this one similarly to gravity, right? To gravity, this is gonna be electric potential energy equals to zero in the same way. Now, let's pay attention one more time. What happens to work? One more time. Remember, if we have the gravity and we have an object right here, any mass, if we're sending this mass from this position to this position, we have to do work, right? We are doing work, right, from zero, right, to this position, correct? So the work done to move the object from this position to this position, from zero, right, to any other position, the work done is equal to mgh, correct? We started from zero. Well, it's not zero. What happens for a point charge, right? That is at that position, and we bring another charge, right, and place it there, right? The same thing as right here, right? We have to do work because they have the same polarity, the same sign, right? So in this case, the potential energy right here, correct, is the work done on bringing this particle from infinity to this position. It's like right here. What should be the potential energy? The potential energy is the work done in moving a particle, this mass, from the ground, let's say, to this position, because the ground is zero. The same thing happens over here. What should be this potential energy? Is the work done on bringing this charge from infinity to this position, correct? Similarly to gravity. Okay, perfect, great. Now let's see what happens if we're looking for the potential energy with several point charges. We found only for 1 point charge, 2 point charges. Now what happens if we have several point charges? Okay, let's do it for several point charges, correct? Let's say we have different charges right here. Okay, this is Q1, Q2, right, Q3, and this is my test charge. What should be the potential energy, right, registered by this charge due to this configuration, right? Well, remember, we use the distance between them. I can call this R1, right, R2, and R3. And you see now the potential energy, right? So it's gonna, the definition gonna be equals to K Q naught times what? In this case, it's gonna be the product. It's gonna be Q1 over R1 plus Q2 over R2 plus Q3 over R3. correct? Over R2 plus Q3 over R3, right? And so on. Correct? It's equals to what? It's equals to K Q naught times the sum of Q sub I over R sub I. Correct? That should be the total potential energy, electric potential energy, correct? K, also we can use, remember, K equals to 1 over 4 pi epsilon naught. Like in the book uses this notation, but it's the same thing, okay? K, correct, Q naught times the sum of this product, Q sub I, R sub I. Okay, now, what should be the work done to create this configuration? Okay, let's do it. The same thing as before. Remember, we have at the beginning this particle, and now let's bring another particle from infinity to this position. What should be then the potential energy? Let's call this Q1, this is Q2, right? And this is R12. What should be the potential energy by this system? Is going to be equals to what? Potential energy is equals to K, right, Q1, Q2 over R12, correct? What about if we have now 3 particles? Then now let's bring another particle from infinity and place it here. Okay, so at the beginning, these are the first 2. Okay, this is Q1, this is Q2, this is R12. Let's place it, let's say, where? Okay, right here. Okay, right here. Now let's call this Q3. Correct? And let's find out the potential energy of the system. Okay, the same thing, right? Now this is R13, this is R1, this is 2, 3, correct? What should be then the potential energy is equals to what? K, correct? Q1, Q2 over R12 plus K, Q1, Q3 over R13 plus what? K, Q2, Q3 over R23. Okay, now let's bring another one. Okay, let's bring it from infinity to this position. Let's say to this position. Okay, so what should be then the total electric potential energy of the system? Well, we have this one so far plus now this new interaction, right? Now we have right here, let's say this call it Q4. It's gonna be Q what 14, right? It's an it's R, actually it's R, right? R14 is gonna be R34, and this is R24. Okay, so for the next one, for this configuration, gonna be what? This plus now plus Q1 K, one more time, K, right, times Q1, Q4 over R14 plus what? Plus K, Q2, Q4 divided by R24, and then plus what? K, Q3, Q4 divided by R34. Correct? And so on. How to represent this condition? Well, this condition is gonna be that potential energy is equals to 1 over 4 pi epsilon naught times the sum of Q sub I, Q sub J, right, divided by R, right, I sub J. In this case, gonna be I less than J, right? It's less than 2 or 1, and so on. Got it? Perfect. That's the case when we're looking for the potential energy of the configuration. Great. Now let's go to the electric potential. It's not the same as electric potential energy, but it's just electric potential. Let's go to electric potential. Right. Let's go to the electric potential. Electric potential, the symbol is V. Okay. Let's go to the electric potential. The electric potential, right, V is defined as the potential energy, electric potential energy, right, divided by Q naught. Correct? Remember, every time you have a quantity divided by another quantity, we create a new quantity. In this case, we call this electric potential. And also it has a new unit. What should be the unit? The unit is called volt. Right? The unit is volt. Right? Volt. V. Or voltage. Okay? Perfect. Now, let's see. Well, we know that from this formula right here, from this one, work is equals to negative change in the electric potential energy, right? And then let's create this condition. Okay, let's divide this by Q naught, and we divide this by Q naught. Correct? But what is this? This is negative the change in potential energy, which is what? Potential energy at, let's say, A, correct? Is at A. It's at B, and because it's a change, right? It's at B, my potential energy at A, right? Divided by Q naught by Q naught. What is this? Well, this is the definition right here for electric potential, right? Electric potential is defined as electric potential energy divided by the charge. Okay, so it's equals to about negative V, right? B, or the potential at B, right, minus the potential at A, correct? Or we can leave it like that, or just we can go to electric potential at A minus electric potential at B. So that's the work done from A to B divided by Q naught, correct? Or we can use the change, right? The change in the electric potential. So we can use either way, right? We can use work also is equals to Q naught, negative Q naught times the change in the electric potential. This change in the electric potential actually is called the potential difference or voltage. Okay, potential difference or voltage. Okay, perfect. Now let's continue. So we have then equations for when we substitute U right here. Look, U is equals to this. So we find for a point charge the electric potential is equals to, again, we have V is equals to U, but U is equals to what? The electric potential energy gonna be K, Q naught, now divided by Q naught, right? I forgot something, R right here, times R, right? It's equals to what? KQ over R. So it's gonna be for a point charge, the electric potential, KQ over R. Correct? Perfect. This is for point charge. For a collection of charges, so the electric potential is gonna be equals to K times the sum, right? Q sub I, R sub I. Correct? This is for collection of charges. What about for a distribution, right? For a continuous distribution, right? The electric potential is gonna be equals to K integral of dq over R. Okay, this is when we have a distribution. Now imagine that we have a constant electric field, right? Constant electric field moving to the right. To the right, electric field is constant. And we place a positive charge right here. Of course, the electric field is doing work. It's accelerating, right, this charge, Q naught, correct? Later, the charge is right here, right? Imagine that the distance is delta x. Okay, we can use x, d or delta x, because imagine this is in the x direction, imagine. Okay, in this case, what should be the potential difference or voltage? Is equals to what? This is equals to, how can I find this potential difference or voltage? Well, Remember, this is coming from voltage, from the electric potential. What is it right here, right? The electric potential V, V is defined as electric potential energy divided by the charge. But what about looking for the change? Okay, change and change. Okay, perfect. So equals to what? Negative work, right? Remember, these two are related. Right here, the work divided by Q naught. That means it's Q naught. But what is the work equals to? Force, right? That product, force, and the distance. Okay, delta X over Q naught. Perfect. But okay. But what is the force? The force is a constant electric field. It's gonna be Q naught, right? Electric field times delta X over Q naught. So what should be then the potential difference, correct? Or voltage equals to what? Equals to the electric field times delta X. Or if we call this distance D, we can call it also D, right? We can say this equals to E, right, times D. The electric field times the distance between these two positions. Got it? So it's gonna be then voltage or potential difference equals to the electric field. This one, the electric field is constant, correct? ED, for example. Perfect. Now, what happens if the electric field is not constant? Well, in that case, we use integrals. Remember, let's use integrals. For example, we have that this electric potential, right? Potential difference or voltage, correct? Is equals to negative the work done from A to B divided by Q naught, correct? Perfect. Now, also we can represent this as negative, right? This change over this quantity, correct? Integral. Let's make the integral in this case. Correct. And what is this? This is equals to negative by the integral of what? F dot dl over Q naught. Over Q naught. But what is this? This is equals to negative the integral, right, of this dot product. Okay, times dl. Right, this is the case when the electric field is not constant in general. Perfect. This one is constant, it's very easy. Correct. So this is equals to, right, the integral of this dot product. This is for the potential difference. Now let's see the curve, the graph that gives us how this potential difference changes, electric potential. Okay, let's do it one more time. Imagine that this is voltage and this is what the distance r, because also depends on r, correct? Like in this figure. This is very similar to electric potential energy, correct? And we have again this curve, right? And that curve. And the same thing as before. We have again electric potential equals to kq over r. And this is the case when the charge is positive. It's the case when the charge is negative. Okay, when the charge is negative, we have this this graph. Correct. Also, look, imagine that we have this charge right here, and we have a test charge moving right toward right this charge right here. Imagine we have something like that. Okay, so the particle moves. Let's take a test charge right here moving in this direction, a test charge. What happens to the potential energy? Well, not the electric potential. What happens to the electric potential? Well, in this case, the electric potential difference increases, right? So this electric potential difference is greater than 0 when this test charge moves toward this positive charge, right? Correct? Because the voltage increases, correct? Now it goes outward, right? This is gonna be decreasing, right? The difference decreases, so it's gonna be less than 0. All right. We can use either way to represent the same condition. This is for positive charge, right? This is positive right here, positive, and we have another positive right coming toward this other positive charge, right? And we create that condition, the same thing as in this case. Correct? Perfect. Now let's go for the last topic for this chapter, and that's gonna be the electron volt, right? The electron volt. Okay, electron volt, right? EV. The electron volt is gonna be just the energy gained or lost by an electron when it moves through a potential difference of 1 volt. Okay, let's do it. Now let's go to potential difference, right? Potential difference is equals to, one more time, change in the electric potential. This is electric potential energy. This is the electric potential difference, going divided by Q naught. Correct? Okay, and from here, let's solve for this electric potential energy is equals to Q naught times change, right, in voltage or potential difference. Okay, now for one electron, it's gonna be the charge of the electron, and when the difference is 1 volt, right? 1 volt is the difference, potential difference, correct? Let's find this energy. What should be the energy? So is equals to 1.6 times 10 to the 19 coulombs, right? Times 1 volt. It's equals to 1.60, right? Times 10 to the 19 coulombs times volts is gonna be joule. Remember, that's the unit for energy. Okay, joules. And this is called 1 electron volt, right? 1 electron volt is equals to 1.6 times 10 to the 19 joules. Correct? Is the energy is gained or lost when an electron moves through a potential difference, electric potential difference of 1 volt. That's the electron volt. Okay, perfect. And with this, we finish this part one for this chapter 23. The next video is gonna be part 2. Okay, see you in the next video. Bye.